The world has changed drastically throughout the past century with the introduction of various types of technologies that intend to respond to the changing demands of human beings. One of the examples is the tremendous enhancement in the field of architecture engineering, with the integration of smart solutions and development of theories led to the evolution of kinetic architecture.
Kinetic architecture is a design direction in modern architecture that captures the attention of architects and academics. It discovers physical reshaping of buildings with the enclosure of technology and innovation. Robotics, mechanics, and electronics utilization in kinetic architecture is crucial to give architects the freedom to design non-conventional buildings. The main parts of the building can now be reformed, and the building itself can be moving. Furthermore, the behavior of the building can be adaptive and interactive with the user and the environment.
Throughout the video, we'll be discussing the aims and objectives of the project. We'll look into the proposed project location and the related climate analysis, and later on we'll go through the design stages and the results of IAS simulation.
The aim of the project is to design a sustainable, dynamic pavilion that responds to the surrounding environment in a temperate climate. Our objectives are to develop a pavilion that effectively adapts to the various weather changes throughout the day and the different seasons in the selected location. Moreover, we aim to provide an adequate amount of sunlight and consider other environmental conditions such as wind and rain. Finally, we intend to build a self-sufficient structure that utilizes renewable energy resources.
The proposed site for the pavilion is Munich, Germany. Munich is the capital city of the German state of Bavaria, located in the southeastern side of Germany. It is the main international destination for business, research, engineering, medicine, and tourism. Marienplatz is a remarkable public square known for its attractive architecture and atmosphere. It is surrounded by significant landmarks that interest locals and tourists. The pavilion can be accessed easily through different transportation methods. A subway station is just 20 meters away, which is a primary option. Another method is using light rail station, which is opposite to the site. Visitors can also use the bus stations, which are 70 meters away. The pavilion is located along two main roads and can be accessed by several internal routes.
Munich is approximately 500 meters above sea level. Its climate is continental, which experiences warm summer and cold winter. In summer, the weather is warm during the day with an average temperature of 18.5 degrees Celsius, while it can be cool during the night when the sky is clear. July is considered the hottest month of the year. In winter, the temperature drops close to zero, and February is the coldest month with an average temperature of -2.5. During spring and autumn, the weather is generally pleasant with less precipitation. The wind speed in Munich is almost steady all over the year. The wind wheel indicates that the speed reaches 20 meters per second, 10% of the hours from southwest, and less than 5% of the hours from east. Munich experiences significant seasonal variation of cloud cover percentage. On average, between June and September, the sky is much clearer, while from late September to early June, the sky is overcast. The annual average sky coverage is 65%. Shown is the sun path across a selected location. Also, the most frequent wind directions are indicated.
The initial idea to design the pavilion was to create a circular, dynamic roof with an opening that could be controlled in size. The idea is inspired by the Arab World Institute in Paris, France, where the building's southern facade consists of innovative, responsive metallic sun breakers that control the amount of light entering the building and the solar gain by closing or reducing the size of the aperture. The design of the pavilion focuses on ensuring the ideal comfortable environment throughout the year, taking into consideration the thermal, wind, and light performance in the selected location. Shading, insulation, and ventilation are the key elements of the design strategy that are implemented as a result of the kinetic feature of the pavilion. Moreover, a renewable energy source is used as a main source of energy in the pavilion.
The pavilion consists of a cylindrical steel structure with a 5-meter height and 15-meter diameter circular roof that has 12 polytetrafluoroethylene fabric panels. They move to form an aperture to provide shading when it's necessary. The base of the pavilion consists of 27 integrated PV panels that slides in a track in correspondence to sun's position and wind direction to generate electricity, provide ventilation, and block undesired wind. It has been noticed in the design that the roof cannot be fully closed due to a gap in the middle caused by geometry. Hence, a new object is introduced to seal the opening when the roof is closed. It can work as a small wind turbine when the roof is open to support in producing energy. For the winter season, 2 layers of glass are introduced into the structure underneath the PV panels to support in achieving comfort. The various weather conditions of the proposed location have been studied for an effective pavilion response. Accordingly, we have developed 9 dynamic strategies to represent the pavilion's functional interaction with the environment. Scenario 1 and 7 represent summer and spring morning. The PV panels are accumulated at the east side and are gradually separated towards the west, toward the south. The roof of the pavilion is closed to prevent heating. Scenario 2 and 8 represent summer and spring afternoon. The panels are centralized at the south and separated gradually across east and west. Scenario 3 and 9 represent summer and spring sunset, where the panels are accumulated at the west and are gradually separated towards the east through the south. Scenario 4, 5, and 6 represent winter. The PV panels are positioned according to sun, and the glass layers slide to the right and left sides of the panels to provide a closed envelope that prevents heat loss and blocks wind.
IES Virtual Environment Simulation software was used to test the performance of the proposed design and investigate the thermal, lighting, and wind effects on the pavilion. Furthermore, to accurately validate the simulation results, an imaginary space shaped as a decagonal prism was created to examine the weather conditions in the selected site. The displayed figure shows the sun exposure on the base case from all directions. The total solar gain is 2.45 megawatt-hour. In summer and spring scenarios, the solar gain is reduced with an average of 65%. In winter scenarios, the solar gain is reduced by an average of 80%. The total PV generated electricity during the studied seasons is 10.87 megawatt-hour. The following part shows the daylight factor and daylight luminous simulation results. The images indicate the reduction in the daylight factor and the daylight luminous. The ventilation analysis was executed based on the most common wind speed and direction in Munich. The following images show the simulation results for the external and internal ventilation. The velocity contour shows that the interior air velocity is enhanced, therefore the indoor temperature is reduced to the desired level. The separated PV panels allowed wind to penetrate and ventilate the space. During winter, the undesired wind pressure was reduced and the indoor temperature was increased to the comfortable level. The PV panels and the glass layers acted as wind barriers.